We're now looking at section 14.3, motion in space. The objectives here are to find r prime of t, the magnitude of r prime of t, and r double prime of t, and think of them in terms of particle motion. Number 2, we're going to find the position, or like the location, vector-valued function if we're given the velocity or acceleration vector-valued function. And third, we'll actually just derive the most commonly used two-dimensional projectile motion vector-valued function and apply it to a couple of physics situations. The first page of these notes explains how to visualize a vector-valued function using a TI calculator. If you have a TI calculator from a different class, you should just go ahead and follow these instructions anytime you want to like do that. Since we are doing this on a computer, I think you should use the slightly better tool, which is called Desmos. Desmos, D-E-S-M-O-S, is an online graphing calculator that has a lot of really good, it's just really good at visualizing things. If you just need a picture of something to get an idea for what it's doing, I would just go to Desmos first. And that's just what we'll probably actually do in the real world. So feel free to use these instructions that are on the first page of 14.3's notes, but we're going to take this two-dimensional vector-valued function and try to get an idea for what in the world it actually does. So we're looking at 1.3 to the t in the x component and t in the y component. So let me show you how to actually look at this stuff in Desmos. So I have Desmos open over here. There's two ways to deal with a vector-valued function in Desmos. First of all, you don't use angle brackets when you're typing stuff in. You type it in as points if you want to see what's going on. And we're doing 1.3 to the t and t. If you just use t, Desmos knows that you mean that this is a set of parametric equations, or that this is a vector-valued function, and then it asks you, what do you want for the values of t? And you can just say, okay, well, I want to go from -10 to 10. And it will just draw the path for you. So this is the easiest way to get just a really quick picture of a vector-valued function in terms of where you're thinking of t as time and the place on the curve as position. The other way to do it is to use a different parameter. If you use a parameter other than t in Desmos, Desmos will be like, I don't know what you're talking about. What do you want from me? And it will say, do you want a slider? So when I do 1.3 to the a power, and then a in the y slot, it says, what's a? And you can say, I want it to be a slider. And when I let the slider go from -10 to 10, it has a play button. And this is super powerful because it lets us see the vector-valued function as a position function where the parameter is time. To make it more clear that you're thinking about this as time, you could call it like capital T, and then Desmos will still like ask you, what are you talking about? It's just lowercase t is reserved as far as Desmos is concerned for like, it'll draw out the whole path for you. Okay. One thing you want to do when you're dealing with an animation in Desmos is these arrows. When you mouse over them, it says animation properties. And you want to make sure that the animation only goes forward. If you let your animation go forward and then backward, which is the default, is to loop forwards and backwards, you can kind of get the wrong idea about what's going on with your vector-valued function. So you want to go forwards. And then you can always change the speed in here if you want. So when I press play, I can see that this vector-valued function, 1.3 to the t, comma t, it describes a path in the plane that kind of like starts down there. My hand is really strange here. Starts down there and then goes up to the upper right. And it's not like it actually stops at that point. If I allow t to get bigger, if I allow t to go up to 20 and hit play again, then it'll show me that, like, oh yeah, it keeps going kind of like off into the distance. To get the path to see more of the path, I have to change it in this way of typing the parametric equations. And to see the point go bigger, I have to change the bounds on the slider. But generally, if you're dealing with a vector-valued function, and you want to just see a picture of it, you should probably be using Desmos if you're on a computer. The TI calculator is totally fine, and if you follow those instructions in the guided notes, you'll be able to get this picture, essentially, but it's a little bit painful, and it's, I don't know, like, you should just use the best tool that you have available to you in this case. In this case, it's Desmos. So let's see what kinds of things we're looking for back in the notes. So basically the goal was to like see just like what does this look like. If you want to change the window in Desmos, you can do that. The window settings in Desmos are up here. Uh-oh, it's cut off on my video. It's right up above the plus sign. There's a little settings wrench, and you can change the bounds to whatever you want. You can also say like, I don't want a grid, or like, I don't want the x-axis. You can make the picture however you want. I don't know what arrows does. Oh my gosh, whatever. It puts arrows on the axes. Anyway, use Desmos, desmos.com/calculator. It's a good deal. Also up at the top there's a share button so you can send graphs back and forth to each other, so you don't have to keep like sending screenshots. It's a good way to go. Seems good. Let's look at the second page. So what do R of 3 and R of 10 mean in terms of our particle motion? So remember, we're thinking of this, we have this vector valued function, R of t is 1.3 to the t. So at time t, R of t tells us the position. Position of what? Well, we're just thinking of some object moving around in the plane. Of course, the the name of the section is motion in space, and so as always, we need to like be a little bit careful with like, wait, what kind of object are we looking for? Are we looking at? Right now, we're looking at motion in the plane. I'll just point the arrow at the right data type up here. So right now, we're looking at motion in the plane. Later, I think we'll get to look a little bit at motion in space. But think about some object moving around on a flat surface. At any time, this vector valued function will tell you a location in the plane. So R of 3 is position at time 3. And R of 10 is the position at time 10. Okay, then we'll find R prime of t. Remember that R prime of t gives you velocity vectors. So how do we do R prime of t? The way we learned to do basically all calculus in section 14.2 is any calculus thing you want to do to a vector valued function, you do it to each component. So to take the derivative of this vector valued function, I'll take the derivative of the first component and the derivative of the second component. Well, what's the derivative of t with respect to t? The derivative of t with respect to t is 1. And what's the derivative of 1.3 to the t? Well, the derivative of e to the t would be e to the t. So this is kind of like e to the t. So you should expect that the derivative of 1.3 to the t is 1.3 to the t. There's a slight problem, which is if the base is not e, you get this extra factor of the natural log of the base. So ln 1.3. ln 1.3 is some number. It's just a constant multiplier. So this is our R prime of t. Okay, so what is R prime of 3 and R prime of 10? Well, we can find R prime of 3 and R prime of 10 by just plugging them in. So here's R prime of 3. It's 1.3 to the 3 times ln of 1.3, comma 1. And R prime of 10 is same thing, just plug 10 into the derivative. Remember early on in this chapter, I showed you a common mistake that students make when trying to find R prime of t. You should not go up to r of t, plug in 3, and then take the derivative. That would be bad. Then you would always get 0, 0, 0, 0, 0 for every r prime of t. Instead, you do r prime of t by taking the derivative of each component, and then you plug in the time. Okay, so if the question was just find r prime of t and r prime of 10, this would be a reasonable answer. But now that the question is asking us to draw these, that means we need some kind of approximate values for these. So I say the word approximate and then immediately write an equal sign. No. So I need to know approximately what 1.3 to the third power times ln of 1.3 is. So I'll just ask a computer to do this for me. I got 0.576 for the first one. (1.3 to the 10 is going to be significantly larger. So what is 1.3 to the 10 times ln of 1.3? That's about 3.62. Ask your instructor about decimal places. When I'm teaching this class, I often, like if we're drawing by hand on a graph, you don't need many more decimal places than this because there's no way that you can draw to this accuracy. Okay, so draw the tangent vector on your graph in a way that the initial point of r prime of 3 starts at the terminal point of r of 3. What does this mean? This means that you're supposed to think of r prime of 3 as a velocity vector, and that this velocity vector makes the most sense if we draw it starting on the curve at the correct point. So let's go back to our first, like the original graph. We know that the original graph looks something like, I don't know, like this. This was r of t. So I think of r of t as describing a curve, and I put these arrows on here every time, and this is wrong. You should put the arrow in the direction that time is traveling. So like as t gets higher and higher, which way does the particle actually move? The particle is going this way. So put the arrows in the correct direction. Okay, then now let's get the tangent vectors on the picture, the velocity vectors on the picture. At time 3, which means at 1.3 to the third, comma 3, we want this velocity vector. So wherever y equals 3, because that's where t equals 3, I'm going to put this vector. So at y equals 3, let's get a different color for velocity. At y equals 3, I want a velocity vector. Oh my gosh, the scale on this. Is the scale equal? I guess it is. Okay, let's do a little better on this picture. Let me get a little bit more accurate picture, because the scale is actually good. Pull up my Desmos graph here. So when y is 10, x is about 14. When y is 8, x is about 8. You can't see me switching back and forth, but I'm just looking at the Desmos graph, comparing to the grid, basically. Looks like when y is 2, x is a little bit less than 2. So the graph is going to look something like this. Okay, just slightly more accurate than before. Then, at the point where y is 3, I need a vector that goes right by 0.5 and up by 1. So where y equals 3, I need to be going over by half and up by 1. That's like this. You should notice that when you go over by a half and up by 1, it's like got a slope of 2, and that's basically like the way to check your work is that it should be going in the same direction that the curve is going at that time. The size, the magnitude of this velocity vector tells you how fast the particle is moving on the curve at that point. But the direction it's going tells you what direction the curve is going. So it should like agree. Like if you get a velocity vector that looks like this, you should say, oh my gosh, no, I mean the curve is not going that way. So the velocity vector should be tangent to this. It should be tangent to the curve. Okay, and then at y equals 10, which is like up here, now the velocity vector goes over like 3.5 and goes up 1. So now it's going to go over like 3.5 and up 1. So something like this. So this is r prime of 10. This is r prime of 3. And I'm thinking of this point here as r of 10. Even though r of 10 is actually a vector, we think of it like a position. And r of 3 is a vector, but we think of it as a position, just due to context. So this is what you're supposed to notice, is that like, yeah, we calculated what the r prime was supposed to be, but when we put it on the graph, we can see that it's actually going in the correct direction. Also, since this velocity vector is larger, it has a higher magnitude, that means that when the point gets to this spot, it must be going faster. Now, Desmos shows us all that when we hit play. The question is, like, so the thing we were trying to see was, here's a point, 1.3 to the 3, comma 3, and here's another point, 1.3 to the 10, comma 10. At these 2 points, by calculating r prime and like drawing it on the little picture, apparently the point is moving slower at the beginning and faster here at the end. Let's see if we can see it. Slow, fast. And the magnitude of that velocity vector is the way that we can like see that on the page and not have to trust the animation to tell us that. So the velocity vector at t equals 3 was just like a little tiny thing that was headed this way, and the velocity vector at t equals 10 was like kind of huge, headed off in this direction, which represents a higher speed. Okay. Took a derivative, plugged in a point. Being tangent vectors, what do these tell us about the particle's motion? This is the velocity. These are the velocity vectors. They tell us not just how fast the particle is going, but also what direction they're going. Compare these vectors. How are they similar? How are they different? R prime of 10 had a higher magnitude. R prime of 10 was a larger vector, which means that the particle was moving faster. Okay. On to the next thing. Find r double prime of t. Okay. Well, we already had r prime of t. R prime of t was 1.3 to the t ln 1.3, comma 1. When we take another derivative, you again do it one component at a time. What will happen is you'll take the derivative of 1.3 to the t, which gives us another copy of ln 1.3. So now I have 2 copies of ln 1.3. They're just constants, though. And then the derivative of 1 is 0. Based on your knowledge of first and second derivatives of positions, what does this vector mean? Well, the second derivative of the position function is the acceleration. So here we have an acceleration vector. This is powerful and important because acceleration is directly proportional to force. And you often would draw, if you take physics classes, you'll draw forces as little arrows. So this acceleration vector, we're finally making it into like, oh my gosh, we can actually draw, like the things that we draw in physics class, we can actually draw them in our math class also. Yeah, so this is our acceleration vector. On to page 3. So what's the summary? The summary is that r of t we think of like a vector valued function. Notice the bold r. We think of a vector valued function as giving us the position of an object. If you think that way, then r prime of t is its velocity vector. I wonder what was intended to go in this slot. I guess there's two ways to think about the velocity vector. You could think of the velocity vector, if you were just looking at the curve, the velocity vector just looks like it's some vector that's tangent to the curve. So probably when this was written, we intended to write that there's a tangent vector here, but that the reason we care about that is that it shows the instantaneous velocity of the particle. So you think of r of t as the position of an object, and r prime of t is another vector, and it's the velocity vector. It tells you which way it's headed and how fast. If you just look at the size of the velocity vector, what that told us is how fast the particle was going. It gives you a number. Remember, the magnitude of a vector is a scalar. It's just a number. And so what's the numerical size of the velocity called? That's called the speed. So if I ask you, how fast are you going? What does your speedometer in your car read? You get a number. It's like 40 miles per hour. But if I ask you, what's the wind velocity? You would say, well, it's 14 miles per hour to the northeast. You'll get a velocity vector, and the speed will just be a scalar number. Then r double prime of t is the acceleration vector. You can think of the acceleration vector I mean, if the object has mass 1, you can think of this as a force vector, whatever mass 1 means. But you can think of the acceleration vector as like pulling the particle around. So let's stick to the plane for now, even though this is all about motion in space, supposedly. We're still sticking to functions that have a two-dimensional vector as their output. Let's just find all these things. This vector-valued function represents a circle. So let's just find all these things about a circle and then figure out like what we actually calculated. Okay, so first to find r of pi over 2 is no problem. That means that t is pi over 2, so we'll plug pi over 2 in for t on both sides of the equation. So r of pi over 2 is 0 minus 1. R of pi over 2, since it's just the value of a vector valued function, we think of it as the position of a particle. It doesn't have to be that, but this should be kind of like your default way to connect it to the real world. Okay, now I want to find r prime of pi over 2. But I shouldn't just take the derivative of r of pi over 2. That doesn't make sense. That just, like, these are guaranteed to be constants, so I would get 0 all the time if I did that. To find r prime of pi over 2, I have to find r prime of t first. So I'll take the derivative of r of t. Oh dear, how do I take the derivative of a vector-valued function? Well, you take the derivative of each component separately. So I'll do the derivative of sine 2t, and I'll find the derivative of cosine 2t. Here's r prime of t. Now that I have r prime of t, I can plug in pi over 2 to get r prime of pi over 2. So I'll have 2 cosine pi minus 2 sine pi. Oh my gosh, I didn't close my parenthesis. Cosine pi is minus 1, sine pi is 0. This I should think of as the velocity vector. There's some object flying around the plane in a circle. This tells me where it is. This tells me which direction it's going and how fast. Then to find r double prime of pi over 2, I need to find r prime of t first, which you get by taking the derivative of r prime of t, one component at a time. When you do the chain rule, you keep the inside the same. It's okay to make mistakes like that, right? As long as you're thinking critically, like as long as you're writing things, you're asking yourself, like criticizing yourself, like is this correct? So here's r double prime of t. Then to get r double prime of pi over 2, I plug in pi over 2 for all the t's. Minus 4 sine pi, minus 4 cosine pi. Sine pi is 0. Cosine pi is minus 1. This I think of as the acceleration vector. Remember, the acceleration is physically, the acceleration vector points the same way as the force. It's directly proportional to the force. I'm just like repeatedly saying one of Newton's laws here without writing it down because I don't want you to feel like it's a physics class. I don't know why I'm not writing it down. But the acceleration vector is like what it feels like, what it feels like, what direction you're being pulled, basically. Oh, it wants one more thing, sorry. It wants the magnitude of r prime of t. The magnitude of r prime of t is, well, take r prime of t and put magnitude bars around it. So here's r prime of t. These, when we're finding the magnitude of a vector, you use the Pythagorean theorem. Square all the components, add them together, and take the square root. I can factor out the 4, and I'll get the square root of 4. And then I have cosine squared 2t plus sine squared 2t is all that's left under the square root. Luckily, cosine squared 2t plus sine squared 2t is 1. So I end up with just 2. This, the magnitude of r prime of t, that's the size of the velocity. The size of the velocity has a name. It's called speed. So if there's an object spinning around in a circle in this way, it has speed 2 all the time. It has this acceleration vector, this velocity vector, and this position vector at time pi over 2. I don't know how much physics you've had. Like, do you know that when you're going around in a circle, your acceleration vector points toward the middle of the circle? So the position vector is pointing 0, minus 1, and the acceleration vector is pointing the opposite way with circular motion. Okay, so sketch this vector valued function along with its orientation. Not too bad. Oh, I zoomed in. I meant to scroll up. So sine 2t, cosine 2t. I know it's a circle with radius 1, but I don't really know where it starts and where it ends and so on. So I'm not ashamed of this. I'm going to make a table. Got r of t is sine 2t cosine 2t. Let's make sure I have the right thing. Yeah. To figure out where it starts and which direction it's going, I'm just going to make a table. Plug in my favorite values of t, and figure out where my position is at those times. At t equals 0, I get sine 0, cosine 0. At t equals pi over 2, I get sine pi, cosine pi? That didn't tell me anything. So I went from 0, 1 down to 0, minus 1. That doesn't tell me if I'm going clockwise or counterclockwise. Okay. Let's try pi over 4. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So here I go from here to here to here. So I must be going clockwise. Nice circle. Okay, in addition, draw the terminal point of the location vector r of pi over 2. Okay, well, r of pi over 2 represents this point. It's the terminal point. R prime of pi over 2 is the velocity vector. Let's look back at what it was. It was minus 2, 0. To draw the velocity vector, we like to start at the position and then go wherever it says to go. So minus 2 comma 0 means go to the left 2 and don't go up or down. This is r prime of pi over 2. And then the acceleration vector, let's get it on the picture too, is 0 comma 4. We also generally draw the acceleration vector starting at this terminal point. Let me get a different color. That's kind of the same color I used for position. Let's do this. 0 comma 4. So I'm going to go from minus 1 all the way up to 3. This is r double prime of pi over 2. So as you go around the circle, you'll have a position, and the position is technically a vector, but we tend to just draw its terminal point, because we're thinking of it as a location. That point will spin around the circle. The velocity vector tells you which direction you're going, and that will be tangent to the path. And then the acceleration vector tells you, like, what force would have to be applied, what acceleration would have to be applied in order to keep you on the path. Here, I'm like spinning around this circle, and I need to turn right to stay on the path. So my acceleration vector is telling me, turn right. Like, go turn that way. I need to be pulled that way, otherwise I'm going to just fly off the circle. Interpret these values in terms of particle motion. Yeah, okay. So this one is the r of pi over 2 is the position. R prime of pi over 2 is the velocity. And r double prime of pi over 2 is the acceleration. Okay, we've done it. We've played around with motion in the plane. Even though the section's called motion in space, that was all like two-dimensional. We had x coordinates and y coordinates. The point is that it doesn't matter how many dimensions you have. Since the components didn't interact with each other at all, everything we did works in 3 dimensions. And technically, if you end up with a reason ever to get more than 3 dimensions, then you can just keep doing it. Like, there's no reason to stop at 3, really. The reason we stop at 3 in this class is that there are awesome facts about specifically 3 dimensions at the end of the class. Also, we kind of live in 3 dimensions, so we tend to stick with that. Anyway, I changed the object up here. We're now talking about functions where you plug in a point and you get out 3 numbers. You get out a point in space. So, what do we do? This one says a particle starts from rest. Okay, so starts, I'm thinking of at t equals 0. From rest, that tells me that the velocity vector at the time 0 is the 0 vector. Now we start at the point 0, 3, 0. So that tells me that the position at time 0 is 0, 3, 0. Notice that each little piece of that introductory sentence gave me some information. Okay, it moves with acceleration. A of t is 1, 0, minus 4. Then the question says, find the location at time 2. So the question is, find the location, that's the value of the function, at time 2. Okay, well, what do we do? If someone gives you position and asks you to find velocity or acceleration, you take derivatives. If someone instead gives you acceleration and asks you to find position, you take integrals. So that's what we'll do here. We'll take some integrals of this acceleration function. We'll get a whole bunch of plus c's, but hopefully we'll be able to figure out what the c's are based on all these initial conditions. So let's do it. So a of t is 1, 0, minus 4. But we can find the velocity vector by taking the integral of the acceleration vector times dt. When you're doing integrals like this, you should make sure that the units match up. So, like, I don't know if you did this in your calc too. Like, velocity over here is meters per second, but acceleration is meters per second squared. Whoa. Where's the rest of the units? T. dt is a tiny bit of seconds. So the units do match. Your integrals, you should think of integrals as like things that work in the real world. They preserve units. Anyway, to do an integral of a vector valued function times dt, you do the integral of each component times dt. So we'll take the integral of 1 dt, that's t, the integral of 0 dt, that's 0, and the integral of minus 4 dt, that's minus 4t. The thing I skipped is all of the plus c's, and that's because I can think of there being a giant plus c vector that has c1, c2, and c3 all included. Okay, just like in Calc 1, it's a good idea to find this c immediately so you don't get buried in c's when you take another integral. Because we took one integral to get from acceleration to velocity, we're going to take another one to get from velocity to position. And I don't want like c1, c2, c3, and d1, d2, d3, or whatever. I don't want any of this. So how do I find c? I find c using the initial fact about velocity. So I'll plug in 0 for the velocity function. I get, this tells me that I'm supposed to get the 0 vector. But this, what I just found, tells me I should be able to plug in 0 for t and get the same thing. Okay, so 0 is 0 plus c. Oh, okay, well, I guess my c vector was just 0. That's okay. So what does that mean? That means that my velocity vector was actually t0 minus 4t, and all the c's came out to 0. Okay, so we got from acceleration to velocity. Now we'll go from velocity to position. Take the integral of the velocity vector. You do that by taking the integral of each component, because that's how you do calculus on vector valued functions, is you do calculus on each component. Again, I'll get a plus c from the integral, and the plus c, I can find what the c is by using the initial condition for the position. So, how will this work? Well, I know when I plug in 0 for t, I'm supposed to get 0, 3, 0. But when I plug in 0 for t over here, I get 0, 0, 0 plus c. So what does that mean? It means that c is this 0, 3, 0. So my position function is actually half t squared 3 minus 2t squared. And this is the vector valued function for my position. what was the question actually? The question was, where is it at time 2? Well, you can find where it is at time 2 by just plugging in 2. We'll get a half of 2 squared, 3, and minus 2 times 2 squared. That's that. So this is essentially 3 Calc 1 problems stapled together, but being able to think of this as one problem and not as 3 separate problems is the key thing in chapter 14. This isn't 3 functions. This is one function. It's just one of these functions. It's a function that has an input of a number and an output of a point in space. Onward. I don't know what's going on this page. I think this page is walking through how to do that problem. Yeah, okay, well we did that. Anyway, usually you don't get initial velocity vectors and initial position vectors. Instead you usually get like speeds or heights or something like that, and it's your job to take all of the individual things that you get in words and drop them into the right places. So the example on the last page of this section is like more in the English language, and you have to do the task of translating it into vector valued functions first and then dealing with it. Okay, so here's our example. The example here is that I've got a baseball. Uh-oh, okay. Baseball hit from a height of 2.5 feet. So I don't want to keep reading. I want to try to like get that into, like translate it into vectors as soon as I can. The problem is I can't really tell if I'm going to need to think about 3 dimensions or 2 dimensions. So I guess I have to finish reading the problem first to decide what kind of object I'm going to think about. Like, are my vector valued functions going to have 2 components or 3 components? So there's a baseball. It's from a height of 2.5 feet. It has an initial velocity of 140 feet per second at an angle of 22 degrees above the horizontal. Use a graphing utility to graph the path of the ball and determine whether it will clear a 10-foot high fence 375 feet away. From drawing the question as I was going, it's clear to me now that I do actually only want to think about 2 dimensions. So even though this is happening in space, I'm going to just think about a horizontal dimension and a vertical dimension. So when I translate all this stuff into vectors, I'll think about like an x-coordinate and a y-coordinate, where this way is x, and over here is x equals 0, like at the start. And then I'll have the ground be y equals 0. So what does it mean if the baseball is hit from a height of 2.5 feet? That means the position starts at height 2.5. From the picture, I've decided that the ball starts at a horizontal coordinate of x equals 0. Okay, this stuff. Initial velocity of 140 feet per second. That's just a number, 140 feet per second. So that tells me that the speed, here's the velocity, here's the speed, is 140 feet per second. We'll need to use this 22 degrees. The way that we'll use this 22 degrees is we'll like draw a triangle and we'll figure out what r prime of 0 actually is. But there's one more piece of information here. The one more piece of information is that like there's something implied by this story, which is and the thing implied by this story is actually a little bit unclear because of this heading. The thing implied by this story is that this happens on Earth. And so there's a fact about Earth, which is that we have a constant acceleration. This isn't just the acceleration at the start, this is the acceleration all the time. The acceleration all the time is downward in the vertical direction at 32 feet per second squared. This is just because we're on Earth. So this is my processing of the problem. We need to do a little bit more processing to figure out what the actual vector r prime of 0 is, but it won't be too bad. We'll just draw a triangle. Okay, so let's get this off to the side. I need a 22-degree angle. I need to be going 140 feet per second. How can this happen? Well, the way this can happen is that the horizontal component is 140 cosine of 22 degrees, and the vertical component is 140 sine of 22 degrees. How can you remember this? Well, when you draw the unit circle, you normally think of the most basic parameterization of the unit circle as being that the x-coordinate is cosine of the angle and the y-coordinate is sine of the angle. So here I'm essentially saying that the x-coordinate is cosine of the angle and the y-coordinate is the sine of the angle, except this isn't the unit circle. I also know how far out I have to be. I have to scale it all up by 140. So I multiply both the x-coordinate and the y-coordinate by 140. So anyway, my initial velocity vector is, like, the initial speed was 140, but the initial velocity is 140 cosine 22 degrees and 140 sine of 22 degrees. Okay, so that's kind of the hard part, and all we've done is read the problem. All we did is we took the problem that was written in plain English and we turned it into a whole bunch of facts about vectors. So let's figure out what r of t is, and then we can get a calculator to draw it for us. So I've got the acceleration vector here. Well, let's go back to some other color. So I'll do the acceleration vector was 0, minus 32. When I take the integral of the acceleration vector, I get the velocity vector. So the integral of this times dt would be 0 and minus 32t, well, plus c. And the cool fact here is that when I plug in 0 for t, I get 0, 0, but I'm supposed to get this r prime of 0. So this c, in the case of like physics with gravity, this always happens. I should warn you that in the case of physics that isn't just gravity, where with like constant acceleration, this trick does not work. But in this case, the initial condition is the same as the c. So I end up with not 0, but 0 plus 140 cosine 22 degrees. And not minus 32t, instead minus 32t plus 140 sine 22 degrees. This is my velocity function. Finally, I can do one more integral to get the position function. So take the integral of the first component. This is a constant, so its integral is easy. I try to never say that things are easy, but in this case, it is. This one has two terms, so to do the integral, we'll have to do the integral of each term separately. And since I just did an integral, I need a plus c again. But because I'm in a nice, like, simple situation where everything, like the acceleration is constant, this initial condition is the c. So I can just add 2.5 to the vertical component, and I'm done. So, what is my final answer? My final answer for the position function is that the horizontal component is just 140 cosine 22 degrees times t, and the vertical component is all this stuff plus 2.5. Now, what did the question ask? The question asked if this is a home run. So the question asked if this gets past a 10-foot high fence that's 375 feet away, and it says get a graph to do this. And I like this. I like this way of thinking. So let's get this into Desmos. Okay, we need 140 cosine of 22. Ooh, how do I get degrees in Desmos? I think there's a little like calculator button down in the lower left corner. Ugh. Okay, well, what is the degree symbol actually? 180 degrees is actually 2 pi. So degrees is 2 pi over 180. Is that right? 180 degrees is 2 pi. No. 360 degrees is 2 pi radians. It's simpler to say 180 degrees is pi radians. 180 degrees is pi. So here's the degree symbol. It's just this number. Okay, so 140 cosine of 22 degrees times t. That's in my x-coordinate. And then I need... Man, this number, this 22 degrees number is going to be really annoying. So I'm going to name it. D is 22 pi over 180. You should do this when you're writing like math or science papers also. If you ever have to say the same number over and over, just name it. Okay, so 140 cosine of 22 degrees times t, and then I had minus 16 t squared plus 140 sine of d all times t plus 2.5. So here the ball starts at height 2.5, and then it rockets off in this direction. Remember that this is just one way to get a vector-valued function into Desmos. The other way to do it is to use a different parameter. So I'm going to do it both ways. I had t as the parameter the first time. I'll use like a capital T the second time. When I switch all the lowercase t's to capital T's, I get an animated version instead. And we'll go from 0 to 10 again. Okay, the question we have is about what happens 375 feet away. And let's just get x equals 375 from 0 is less than or equal to y is less than or equal to 10. So this is our fence. And it looks like we are going to clear the fence here. Nice. Not by a lot, but good enough. And it would have cleared the fence at 400 even. Cool. So, what is the computerized stuff you're supposed to learn here? First is that the degree symbol is actually a constant number. It's this number. So if you ever need to write the degree symbol and you don't know how, this is what number it is. It's pi over 180. The other thing is, if you have a number and you have to write it a lot of times and it's ugly, give it a name, and then just write the name. And you can do that in Desmos, and you can do that on your homework too. Then this is something from before, but to recall, is that if you use t as the parameter in a vector valued function in Desmos, it draws the path. If you use any other letter, even like a capital T, you get an animation. You can see the ball. So it's pretty cool. This doesn't look like a 22-degree angle. That's because we don't have a square. Like, it wasn't equal scale. Now you can see it's a 22-degree angle. So that's pretty awesome. Okay. A couple follow-up questions. How could we use r of t to find the maximum height? The reason it's this r of t, this vector valued function here, is nice is that if you have questions about height only, you can just look at the height part. The height is one of the components. So if you want to find the maximum height, you can just grab this and find the maximum of this. If you want to find the time when the ball hits the ground is a fact about height. So again, you can use just the height component. Yeah. If you end up having questions about the horizontal distance traveled, you use the horizontal component. If you have questions about the height, you use the height component. Having a vector valued function splits up the function into its two components, and you usually care about like one of those components at a time. So that's it for section 14.3. The basic idea is that whether you're in the plane or in space, either way, you still might only use two components in your vectors. Here, baseball is played in a three-dimensional space, but my problem, I was able to like draw it in a way that I only had to think about two dimensions, horizontal and vertical. So don't go all out and make 3 dimensions when you only need 2. Second, anytime you need to do calculus, you do the calculus to all the components. And then finally, all of your like basic physics calculus knowledge, like where you get to take derivatives with respect to time to move between position, velocity, and acceleration, or integrals with respect to time to go from acceleration back to velocity, back to position, that all still works. The only thing that's different is that the constant is a constant vector, and the initial condition is an initial condition vector. And so it's a little tricky to figure out where to put everything. You should have if you've taken a bunch of physics, you should have a complaint about this problem, which is, oh my gosh, there's formulas that just do this for you. And that is the right physics way to think about this problem. But if anything about this problem changes, like we add wind resistance, or like gravity changes when you get too high because we're talking about a different scale where like the projectile is going a really, really long way, so that we don't think about gravity as constant anymore. If you change anything about the situation, then the physics formulas basically fall apart, but the vector valued function stuff, where you like do the calculus, that process will always work. So we have you use, I mean, this problem can be solved by simple physics equations, where you just like memorize the equation and use it, but that's kind of not the point. In the math class, we want you to be able to build the equations using just first principles, because then you can do that even in complicated situations. So that's 14.3.